Okay, that's for next Thursday. So today the plan is that I think I probably moved too fast last time, so we didn't actually go through examples on single-stage amplifier analysis. So I would like to briefly go through two examples as to what kind of questions you might be faced in terms of design problems or calculation problems. How does one approach when you're actually faced with a particular circuit? So last time we only have time to go through one example. Today, so I would like to probably go through some design examples as to what are the approaches or directions as to how one approach a problem. So we're going to go through two examples, and then one on common gate stage, and the other is on common drain structures. This is mostly to address, this is especially to address a body effect. So we didn't actually address the effect of, I think I talked about body effect a little bit, but I'm just going to explain how that affects particular circuits in terms of its analysis. Why do you need to take care of that? Or consider body effect, the effect on circuit analysis. So then we're going to move on to chapter 9. As I said, we're going to talk about there's actually in chapter 9, let me outline a little bit. So in chapter 9, we're going to talk about one of the key structure, which is called the cascode structure, and then the other is called the current mirror. So let me outline what is next so that you get a sense as to where we're at and what we're going to do in the following semester. So in I think chapter 10, this is the future. So what are the key topics we're going to talk about? On chapter 10, we're going to spend a lot of time on one of the key topics called the differential. So one of the key concepts is the concept of having differential circuits rather than single-ended circuits. So we're going to compare the concepts. We're going to spend a lot of time talking about differential. And differential pair is one of the simplest structures in constructing differential amplifier. We're going to talk about that. And lastly, on chapter, I believe, 11, we're going to talk about frequency response. This is a very big topic. So these are the things that is coming in the future. So you get a sense as to where we stand. We have the basic building block of single-stage amplifier. How does you combine them and to construct certain structure which is useful in terms of larger circuits? And then you address different issues. One is to talk about this. This is to increase analysis on speed, because we didn't spend much time talking about speed of the circuit or bandwidth. So this is just to expand direction as to which are the key components in addressing or analyze a circuit. And this is one of the structure which allow us to minimize noise. So we're going to talk about that. So this is what we're going to cover until the end of the semester. So you sort of know where we stand. So it's probably at the middle of the midterm, after midterm. So we're probably at the middle after having all the single-stage amplified analyzed or introduced. So next we're going to go into more complicated issues and structures dealing with these type of issues. So as I said, this is to address noise. Okay, one is to address noise, the other is to talk about speed. So let's come back to single-stage amplifier, a common gate stage. So let's say I give you a common gate amplifier. Looks something like this. So as I said, there's two types of problems. One is that I give you all the parameters. You calculate what happened to the circuit. That's a basic, straightforward circuit analysis problem. So circuit is given with all the parameters given, and you calculate what happened to the circuit, finding out its input-output resistance, finding out its overall gain, and its biasing condition, that sort of things. The other type of question is called a design problem, meaning that I give you a structure, and you determine the parameter in order to fit the specs being set. So we're going to go through an exam problem as to how one approach this type of issues. So in the future, you'll probably mostly be faced with design problems. And then you go back and do analysis to make sure that whether that fits your first order assumptions. So let me just give, this is with a bias. And so it's biased with a resistive network just to make our life easier. And the input terminal is coupled, so input is coming in here. And this is my output terminal. So it's a common, based on this, if I give you the circuit, you're looking at where the signal coming in, where the signal goes out. You know that it's a common gate structure. The gate is being biased by this resistive network, and input coming in from the gate, output going out at the drain. So knowing where your input output are, you should be able to define which operation, which type of architecture you're actually using. So this is a common gate stage. We want R1 is set to 500. And the target, let me give device parameters, M1. So for this transistor, we know that the technology parameter give us 100 microamp volt square, and it has a threshold of about 0.5 volt. Okay? And then your spec tell us VDD is 1.8 volt. It's typically being defined by technology. The voltage can be, or supply voltage is a system provide level, so 1.8 volt. And then I have so two specs, which is the power budget. Power budget meaning that the maximum power can be dissipated by the circuit. I misspelled it, but. So the power budget is set to 2 milliwatt. And then I need to design to meet a certain spec. And most, as I said, in most of the common gate stage is used for taking in current signal or impedance matching. So let's say if this is for impedance matching, meaning that I'm setting my Rn to 50 ohm. This is to say that this is defined for impedance matching. So typically, when your input is connected to an antenna is 50 ohm, you want it to be balanced so that you get the maximum power coming into the system. That's called impedance matching. So basically, I want this to match whatever my antenna resistance is. So that's the spec for this circuit. So let's move on to what you need to determine. So basically, you need to know what your biasing conditions. So you need to determine RG1, RG2 for setting this biasing condition, right? In order to meet this criteria. The other thing we need to know is that you need to design. I already know R1, so the next thing is that I need to design M1 so that W over L, the size of transistor. So there's 3 unknowns are needed. You're setting, this is RG1, RG2 is the parameters you use to set up VG, and device size is how you set up GM. So let's do some, so first of all, for power budget, allow us to determine what is the maximum current that's being flowing through the system. So let's say for power, so you start with power, typically you start with your boundary. Use yellow. So let's start analysis. So typically you start with your boundary, your power dissipation is your limit, is 2 milliwatt. So I know that the maximum power is available, total power available is 2 milliwatt, 1.8 volt. So that's 1.11 milliamp. So you have two branches of current. One is IDQ. The other is the biasing current, let me say I1. So this is the total amount available. So this should be your IDQ plus I1. The total current should be smaller than your biasing current in I1. So you can separate between the two. You make a decision. So typically what we want is that you want to keep your main current. This is just biasing, especially when gate current does not taking any, gate does not taking any current. Therefore, you don't actually need too much current for biasing. Therefore, you want to keep it as small as possible. So I make a decision so that I set. This is arbitrary, so you can do your own design. This is just a design solution. One of the design solutions, as long as it does not exceed the boundary. So I'm using more than 90% of the current for biasing. Let me set my IDQ to 1.1 milliamp. Therefore, my biasing current will be left to only 10 microamp. That means that I would need large resistors to set this up, but that's fine. Depending on your design, your boundary in terms of determine how do you get this resistance. So there might be some trade-offs, but this is just one of the settings that allow us to go in to further design this. And then because this is the case, I know the voltage at this particular biasing point, which is VR1. So therefore, VR1 will be IDQ times my resistor R1, which is 500 ohm. Therefore, it gives me 550 millivolt. Okay, so I already know the current. The other thing is that I need to determine, so now once these are defined, the next thing is to determine W over L. Before determining W over L, you should know that how does one determine W over L? You start with your requirement on GN. So we know Rin, I should say. Because Rin, in this case, if you're looking in from here, is 1 over GM in parallel R1, right? So we assume that this, you can actually include R1 or without, but it's approximately, so this will give you, will still be approximately 50, very close to 50, because it would maybe 10% difference. You can make it more accurate. I'm just assuming that this will be much, much larger. This will be the dominant resistance. Therefore, we know that GM, there's various ways of expressing GM. In this case, I know my current, and let's say, okay, so once I know this, I could use different expression of it, determine whether my W over L is, or you could determine your size. So the way to do this is that you want to set your biasing conditions. So we're going to set a VOV, a overdrive. You can set your own overdrive depending on what is the biasing condition. We already know that this is 0.55. So you should design where your VG should be, determined by the overall scope of your biasing condition. I know that my overall voltage is 1.8 volts, so somewhere in the middle would be good. So I'm setting my overdrive to about 0.1. That's 11 millivolts. So let's say I'm setting an overdrive, then this will give me, let me rewrite this. Because GM is, you can set it up with 2ID VGS minus VTH. We know that GM can be expressed this way when, this equation is used when W over L is unknown. Because we don't know what WL is yet. But we know the current and we know the GM. Therefore, this is known. We already set it up to 1.1 milliamp. This is set by requirement of Rn. This is 1 over 50 ohm. So you insert the number, you get a definitive overdrive. This is the overdrive. This is VOV. So we know that VGS minus VTH, by these two numbers, we should be able to get your overdrive as to 110. Let me make sure I got it. 0.11 volt. So you get this simply by setting up my current. And GM, when this current is fixed, GM is fixed, your overdrive is fixed. So once this is fixed, then you can go back to determine. Remember, what we need to know is the W over L of this device. So you go back to the current equation. IDQ equals to 1/2 mu n Cox W over L VGS minus VTH. I'm just going to use the first order equation in saturation. So this is known. This is 0.1 milliamp per volt. This is 0.11 volt. And this is 1.1 milliamp. So it will give you one answer of W over L. Right? This is known, so we can get W over L. The ratio is 200 over 0.11. So it's a fairly large transistor, wide transistor, I should say. And this is typically not a good number because just by, I didn't actually define, but based on the VDD, it's supposed to be a 0.18 micron technology, meaning that your lens probably is the smallest lens you can draw is 0.18. So you want to make sure that, let's say if this is 0.18 micron technology, this is just based on VDD at 1.8. Suggests that your gate length should be larger than, so that is to say this is something that will violate design rule because it cannot be made. Therefore, you could actually shift it to 400. So a better answer will be this. So this would then be larger than your minimum length. Okay? So I'm just summing up all the biasing voltages. This is VGS. So it's overdrive plus a threshold, right? You put it over. VGS is, let me write it down. This case, VGS equals to threshold plus the overdrive, VOV. Okay? Yes? I total 是的这个两个相加。是从这边来。假设你要这样接的话，就是这个。I total. Yes, yes. Supposed to be 就这两个相加了。你可以想象它就可以接在一起啊。It's the same terminal. If you shift it. 整个电路对，整个电路。它的 dissipation 就要考虑你消耗在 bias 跟消耗在你自己本身上面。 the total the dissipation of this single circuit. Okay? Good? Okay, so the next thing we're going to talk about, so then you determine RG1, RG2. So first of all, we know that therefore RG1, RG2, there's a ratio. The ratio between the two should be 1 point, I should say, RG1. The ratio between two should be 1.16 over 1.8. So we know that for this voltage divider, let me see, RG2. Okay, so we know that it has to fulfill this ratio in terms of voltage dividing. And the other thing is that then the absolute value of this resistor is RG1 plus RG2 should equals to I1 times, VDD divided by I1. So the total current, total resistor, the sum of the resistors should equals 180 k ohm in order to fit I1. In order to set I1 to 10 microamp. If you set I1 to 10 microamp, this is what you get. And then we could find out the absolute value. Therefore, RG1 is 64 k, and RG2 is, you can do the exercise on your own. Did I get it right? Maybe. 180, right? Okay? So this is just as I said, it's a design problem. Your answer might not be the same as mine, but the only thing you need to do is to make sure that it fits its spec. So we go back and check. It can be a good or bad design. There's following judgments on that. But you set up to make sure that it especially fit the spec. One is input resistance. The other is power budget. Okay? Questions? Good? Okay. So I'm going to quickly go through another example on common drain circuit. So let me give you an example. So let's say if I have a source follower that's common drain. I need to determine its biasing current in order to determine its output resistance. So let's say the circuit looks something like this, VDD. And then I could actually bias this circuit this way. I'm using sort of like a self-biasing scheme to set the biasing voltage. Okay? So this is M1. And input coming in here, and output going out at the source terminal. Let's say I want to set okay. So the design problem is, we're going to consider two cases. One is that you include body fat, the other is exclude body fat. And we're going to see how much discrepancy there is in your design solution. So let's say I'm just going to set it up first. So this is 1 k ohm. And this can be an arbitrary number. This does not really change too much, only in terms of speed. So you don't actually care. There's no DC current flow. Okay, and this is 1.8. Let me see what are the parameters. So we're going to give you threshold. Okay, once again, mu and Cox. I'm going to use the same mu and Cox, which is 100 microamp rho square. And it's VTH 0, meaning that it has zero bias, zero body bias. Okay, it's 0.4. So first of all, let's ignore body effect. I'm going to introduce the body effect coefficient when we include it. So the key is that if you ignore body effect, we can actually find out what is the corresponding GM to find the transconductance, because this would then determine your output resistance. Remember, if you're looking in from here, RL will be RS in parallel GM. Therefore, GM will determine the characteristic of this source follower, the key performance factor of the source follower circuit. So let me use the yellow. So when you ignore body effect, first of all, we need to find out what is its, oh, sorry. And also, we already know that it's set so that the current is at ID1. ID1 is set to, the current is already set to 1 milliamp. Therefore, this is the case, then I know the overdrive, I should say VL, at DC level should be 1 milliamp times RS, which will give me 1 volt. And the overdrive of the circuit, I should actually set it up. The overdrive of the circuit is VOB, is VGS minus threshold, which is, what is your gate voltage? Anyone knows? What is the gate voltage at steady state? VG. What is it? No one knows. DC, this is open. Is there current on the resistor? No, therefore this voltage is 1.8 VDD. Minus minus source voltage. I know that output is my source voltage, so this is Vs minus threshold. This is actually VL. I should just write it down. Yeah. So it's VDD minus VL minus VTH is your overdrive. So I know my overdrive is 0.3 volt. So I could actually get my GM, transconductance GM, without knowing the device size, because this is the design. I already know the current. So whatever W over L will give this current under the circuit. So this will be 2ID. As I said, without knowing W over L, you should be able to use this equation to get your transconductance, which is 66 milliamp per volt. Okay? So this is fairly large transconductance. Okay? That's good. So the next thing is that this is because we ignore body effect, meaning that we assume the threshold voltage does not shift because of this high source voltage. But what if we include that? So as I said, to include body effect, we need to know how does one calculate the shift in threshold. So let's give the equation. The equation is the actual threshold will actually increase because I will expect my threshold to increase because this voltage, VSB, is no longer 0. You have a raise of threshold. So gamma, let me review the equation. So VSB plus 2 phi f minus 2 phi f. So that's my body fed equation. And we need two parameters, which is gamma is 0.6 volt and a half, and then 2 phi f. This is typically 0.8 in most cases. Okay? Yes. Yes, yes. 因为我们 ignore body effect. Sorry, this is, let me just highlight it. This is BTHO. Did I make a mistake? 0.4应该是0.4吧 Sorry. Yeah, it's 0.4. So for this number, that may be wrong as well. So this will be 2. Let me readjust this. So this will be 2 milliamp divided by 0.4. And that will be 5 milliamp per volt. Right, you're correct. I'm coming. Why do I get a point? For some reason. Yeah, made a mistake. Good. Okay? Yeah, it's actually much simpler number. So this would then suggest that this is actually easy. This will then suggest that you have a, did I get it right? Inverse of that. Correct. This will then suggest that your 1 over GM is 200 ohm. Right? So that's your output resistance at a level of 200 ohm. In parallel with this, and then will be somewhere a little bit higher than 200. Okay? So let's look at, well, once you include, what is the impact on its overdrive, mainly on overdrive. So what we want to do is to find out the threshold, the actual threshold when VSB is no longer 0. So we know that source to body, source, sorry, I didn't highlight, body is here. Body is by default connected to ground. This is body. So I know that body is ground, source is at 1 volt by this setting. That is to say, VSB equals to VSB equals to VSB equals to 1 volt. So you simply insert that in. This will be 0.4 plus 0.6 square root 1.8 minus 0.8. And then we get the threshold slightly higher. Okay? What is the implication of this is that you will then have a much okay? So then in this case, you will actually have, the implication will be to sustain this, the same amount of current, it means that you would then need a much larger W over L. From this, we can actually go back and calculate its W over L. But in this case, what happened is that your overdrive will then be, as we did, your overdrive will be 0.8 minus 0.67. Therefore, we'll have a much lower overdrive. I should say 1.3, correct? So based on this circuit, you would then have a much smaller 1 over GM because overdrive is at the bottom. So 1 over GM will be higher at the cost I should say GM will increase at the cost of increased WL. The reason why we don't see this is that we didn't go back to check under this balancing point, under this 1 milliamp. If I'm considering body effect, you would then need a much larger W over L. The reason is because of this equation. Let's say this remains the same, but your overdrive becomes smaller, therefore your W over L needs to be higher to sustain this same amount of current. So even though we get, you see that including body effect, to keep this, meeting this standard, you would then need a much larger transistors in order to meet the same results. So if you go back to check W over L, including body effect would then request a much higher, much wider transistors. Okay? So that's the main difference when you include it, meaning that your overdrive will be less, causing you to increase your W over L in order to make sure that the current level is the same. Okay? Good. So you can do the exercise to find out for this two design to meet the same requirement, include or does not include, what is the request on W over L? VSB, because the source voltage is VL. VS equals to VL is 1 volt. Body is ground. Body always ground by default. If you do something, you can actually have something called a source body tied structure, but that's a costly solution. And then there will be complications if you connect source and body. By default, and I want to mention one thing just to give you an overview. In most of the integrated circuit, remember we said that for transistors, your body, especially if we already introduced the sort of twin well example. I don't know if you remember. We have a little bit of time. If you look at a CMOS technology, this is called a twin well, just to do some twin well process. You start with a P substrate. And then you have M plus, gate. Right? And P plus, gate. So this, from the left, is the N channel, right is the P channel. And what happened is that you would then have N wells. And these are P well. But because P well is connected to P sub, therefore you only have one substrate. So all of them are connected together. So that's your to ground. So that's your body. Body is connected through here to here. You can actually do implant within well, but it's still the same. So if you're doing twin well process, this is called a twin well process. For N-channel device, there's only one solution. Your bodies, all the bodies, multiple transistors, like billions of transistors, all the bodies are common to ground, or maybe whatever minus voltage. Because you only have one choice. Everybody is grounded. Everybody's body is grounded. Even though I have this well, but this well is the same potential as substrate potential, therefore they have to share the same node. Everybody share. But for PMOS, I can actually build wells if you need to. So the main difference is that for PMOS, the contact is a substrate contact, it's body contact for PMOS. Even though I'm only having twin well process, this is N plus. So this can be individually made, meaning that if I'm making another PMOS here, I could create another N-well, and P plus, P plus. Okay, so this VB1, VB, let's say this is VB1, 2, and 3. So VB1 can only be 1. There's only 1 because they're common to substrate. But M-well is not common to substrate. Therefore, VB1, VB2 can be individually therefore, this well can have a different potential from this well. So if that's the case, then you could do what we call the source body type. We'll then have independence of my biasing condition because this well and this well are not connected together. So there's a main difference if you're doing twin well process. Of course, there's like triple well to surround it so that you can have independence. But anytime, so just to give you a sense, if you're having a twin well process, this simply implies that your N-channel transistor will not, your transistor, the body of your transistor is not within your control because it's shared by everybody. But the P-well, if you're doing PMOS, so this is to say that if I'm doing PMOS transistors, I then have the choice of individually biasing this body. This is VB3. I have 2 transistors in different wells, then this will be VB3. I will then have the flexibility of individually biasing them. Okay? So if I want to avoid body effect, one of the things can be done is to do this. I could short source and body so that VSB equals to 0. I could short them so that it will always be 0, and there will be no body effect. But this comes with the price. You need individual wells. So this 2 transistor needs to be in different well. So it takes a lot more space, if that's the case. Okay? Any questions on the previous discussions? 我稍微简单讲一下，就是body effect 最主要的影响就是它会降低你的 overdrive， 因为我们的 threshold 会把，你看我们本来是 0.4， 它会降了差不多1/3哦，所以你的 overdrive 降低的情况下呢，代价就是要有一个比较大的 transistor。等一下会去看，你可以回去推这个 transistor， 就你在假设你要 design 达到不考虑 body effect 的时候，算出来的 transistor size 这个需要大很多，就表示你要有更多的空间去让这个电流流，因为你 overdrive 不够。去 sustain 这个电流，所以这个主要是 body effect 的效应哦。那通常啦，因为 body effect 很讨厌，就是说它会吃掉你的工作空间哦。大部分情况针对 source follower 主要是这样子。所以呢，如果你要避免它的话呢，就是你可以就是故意把 source 跟 body 接在一起。那这个是必须要建立在这个 body 的 potential 是独立的，就是它是跟别人没有共用。如果它有跟别人共用的话，那你就没有那个空间。所以我刚刚讲，如果你是用我们叫做 twin well process 的话，你的 body by default 就大家一起共用。那只有 PMOS 不是共用，所以 PMOS 你有这个空间，你可以画大一点，你可以把2个分开。所以你可以一人一室啦，就是 PMOS 上你就可能比较有这种一人一室的空间，可是 N 就没有，大家就是共用洗手间这样子，你懂我意思？所以这个意思就是说，我有这个空间，我一人一室，我们2个这个的 bias 是独立的，可是这个就不行，所以这个的话就是大家共用洗手间的概念。OK， 你的那个 body contact 就是共用。那所以独立有独立的好处，独立的好处就是我可以独立去决定我的 body bias， 我要把它设在哪里就设在哪里，这样的话就可以避免 body effect 这样子。OK， 好。Let's take a break for 10. We come back and then we're going to venture into chapter 9 and talk about cascade structure. Very interesting. Okay, so we're going to enter into chapter 9, which we're going to introduce this. We're going to talk about two topics mainly. One is the cascade structure, the other is current mirror. So for today, we're probably just going to start on introducing what is a cascade structure and what is the purpose of having a cascade structure. So typically, when we use a cascade structure, you mainly wanted to substitute something. You wanted to have a more ideal current source. You want to deliver a more ideal current source. More ideal current source meaning that, typically meaning that it has a flatter input output resistance. What is an ideal current source? If you look at its current and voltage relationship, ideally, you want it to be flat. So this is an ideal current source characteristic. If you use an ideal current source, it should be flat, meaning that the output resistance should be infinite. That's what an ideal current source is. But we know that if you're using a transistor, for example, bipolar transistor or MOSFET, because of early effect, what happened is that if I'm using a single transistor, it will look something more like this. So if I'm using a transistor, it will look something, this is like a single transistor. You use a transistor to simulate its current voltage relationship. It will look something like this. The slope will be RO. So what we want is that we want to make sure that if I'm not satisfied with this output resistance, what can be done is that how do I make this slope coming down? So you want this slope to be somewhat here. So this is what we want in a cascade structure. So in a cascade structure, you would then push down the effect, increase the output resistance mostly, simply by this feedback loop we talked about when you're using a common gate structure in between resistors. So you get something more like this. Okay, so that's basically what we want to do. The other thing is that you can do an amplifier. So the cascade structure topology, mainly the first thing you see that is that it will then effectively increase. So it has one of the main features of a cascade structure is that it effectively increase output resistance. So this can also be beneficial for amplifier circuit. If you think about an amplifier, typically we use a voltage control voltage source. But if you use something called, I think most of the transistor amplifier, it's more similar to a transconductance model. Let's use a transconductance model. We call it transconductance two-port model. If I try to explore my circuit into any amplifier using a transconductance two-port model, typically we use voltage amplifier two-port model. You can use transconductance two-port model. It will look something more like this. It will be a Norton equivalent on the right. Rather than having a voltage source. So this is called a transconductance two-port model. It will then include three key parameters. Also, input-output resistance. And instead of having a open circuit voltage, it will be GMS. Okay? So a transconductance two-pole model consists of a transconductance instead of a open circuit voltage. So GMS is defined as IO versus Vn. So let's say if this is my output current when VL. S stands for short, when it's short. IO when it's short. When this is short, you see the whole overall current. Okay? Let me just be specific, VL. And this terminal, the voltage across is VL. So if you look at a transconductance two-pole model, what it means is that your voltage gain, if in this case, my voltage gain, if I go back to look at voltage gain, it will be GMS times R out. So for the amplifier application, GM is the way, remember the sensitivity when you modulate the current. So this is typically determined by transistor design, W over L, biasing current. And if I can boost this, it simply means that my overall gain can be boosted. So as an amplifier, gain can be increased by RL. If my transconductance are the same. So if I keep the same transconductance, if I can boost my output resistance to a high level, I can also get a high gain single stage amplifier. So that's the reason why we want to introduce cascade structure to boost. By the boosting of effective resistance, I could actually increase my overall voltage gain. Okay? So let's look at its structure. So as I said, the main reason is to deliver high output resistance. So let's look at a cascade current source. So let me just write it down. So I'm going to just write down a cascade. So if you want to deliver a cascade current source, depending on whether it's for loading or I should say for pulling up or down. What I mean by this is that if I'm using this current source as a pull-up, meaning that it's connected to VDD, so pull-up is to VDD, to high voltage. Pull-down is to ground. Let's just say my lowest voltage is ground. Okay, so you could actually have, if I want to deliver, for example, current source like this, let's say for source follower circuit, that's a pull down. Pull down loading, you put it in the bottom, or sinking loading. If I'm doing circuit like this, a common source amplifier, so this type of current source is called I2 is called a pull-up. I1 is called a pull-down. Okay, just to give you an example. Okay, so how does one realize this? And let's just write a pull-down example. So for pull-down, a cascode structure will look something like this. I would then have two transistors stacked together with a fixed bias. Let me have it, VB1, VB2. This will be similar to a I1. Okay? I'm just drawing the BJT. You can do the MOSFET version as well. For I2, I2 pull-up will be something more like this. You're going to use PMP instead. So this will be Q1, Q2. Okay? Q4, Q3. I don't know. Did I label it correctly? So typically you want to have 1, 2, 3, 4. There's a lot more transistors. So this will be equivalent to a pull-up current source, I2. So this determine, depending on whether you want to pull it up or pull it down, you use the MPN or PMP. So you can also draw the MOSFET counterpart. Let me just draw it over here. So if you want to do the MOSFET, this will be N channel, 2 N channel to ground, M1, M2. Okay, for PMOS, for pull-up, you use PMOS. And to do a current source, you typically want the bias of your gate to be fixed. So this simply means that it's a DC bias. All the gates are DC bias. Okay? So as I said, this type of cascading structure is to enable the increase of output resistance. So let's look at how does your output resistance changes. So one of the key is that the key performance factor is this. You want to press it down. You want to make sure that the slope actually decreases. So the key performance factor is actually R out here. Right? You want to find out what the RL is for these two cases. So let's look at a MOSFET version first because it's easier. So for a cascade, let's just say for a MOS cascade current source, it looks something like this, right? You have two transistors. The labeling will determine, depending on what kind of fashion you want from the bottom to the top. So you start with M1, M2. M1 is the most bottom one. M2 is on top. And then you bias this. Let me just follow my convention from bottom to top. So what I want to do is that I want to figure out what is its output resistance. Looking down from drain. So remember our discussion on common gate structure. This will be very similar to, if you view it, you can actually view it as, this is a constant bias, therefore you actually see RO1. So what happened is that your circuit, you can simplify it as this. M2, VB2. The bottom circuit will simply be, you only see the effect of a resistance. So I'm seeing RO1, right? So this is equivalent to this. So I'm looking in from here for output resistance. Go back and look for common gate at its output terminal. So your output resistance, and go back to check the equation, is 1 plus GM RO. This will be transistor number 2. And amplify RS, whatever you look at underneath. So remember, if this is an RS, this is RS. But now it's RO1 plus RO2. Go back to use the equation of common gate output resistance when you have source resistance at the bottom. So this is self-source resistance. OK? So this will be approximated by, assuming that you ignore the 1, you ignore this, then it should be GM2 RO1 let's say in most cases, because I'm using a single branch transistor and also single branch, and typically if your size is the same, so you can assume that if, this is not necessarily always true, but if GM1 equals to GM2, RO1 equals to RO2, use 2 identical transistors, what happens is that you will actually get something similar to GM RO squared. OK? So you actually flatten it out by, or if I'm rewriting this, by a factor of GMRO. This is how much it flattened down. And it will flatten down by a ratio of GMRO. Originally, if it was 1 transistor, it's a 1 RO times by a factor of GMRO. So it's a very effective way of increasing output resistance when you do the stacking. So that is why we spend a lot of time talking about impedance transformation, because it's very important, especially in this type of architecture. We can also look at BJT versions. There is slight difference in BJT cascode structure, simply because of the introduction of RPi. BJT cascode structure for pulling down current source will be something like this: Q1, Q2, and then VB1, VB2. OK? So we can also simulate this as to, this will be equivalent to a common base structure, Q2, RO1. Right? And then we're also looking in for its output resistance. So you go back and check the equation. So I'm using a already simplified version. RL is approximately GM2 RO, because it's the second M2 transistor times RO1 in parallel RPi. And we know that in this case, RO2, so there's 2 scenarios. Let's just discuss that. So for RO2 to be a RO1, sorry, output resistance, much, much larger than RPi, what happens is that your overall R out would then be beta RO. Let me rewrite this. So this would then be GM2, RO2. Because RO1 is much, much larger, so you see R pi. And therefore, it will be GM R pi, therefore, is beta RO. Let me just say that for bipolar version, GM1 as always equals to GM2 equals to GMY. What is the GM of bipolar? You still remember? I should say approximately. Yes. For GM is ICQ, right? So it basically has, there's slight difference in current because emitter current and collector current are slightly different. But this is ICQ. So it's a single branch. There's a slight beta effect. But if you ignore the effect of beta, maybe less than 1%. So this branch, meaning that its collector current is almost the same. Because it's almost the same, so it should be almost identical in all cases. In MOSFET, it's harder for me to say that. It's because in MOSFET, you could use W over L to adjust so that not necessarily both of them has the same GM, even though their current can be the same. The current through a cascade structure, remember, I want to say it again. ID1 equals to ID2, equal to the same biasing current in this case. And this is also about the same. So in this case, IC1 is approximately equals to IC2. And it's a fixed current, fixed branch current, if you ignore the base current effect. So that is to say, because GMs are the same, and RO, because current is the same, this is because IC is the same, almost the same. That is to say, RO1 equals to RO2 equals to RO. You don't have any margin in adjusting RO because if you're using the same technology, it's the same early voltage. There's no adjustment. For previous case, of course, you can have different channel lengths. Therefore, its modulation effect can be different. But for BJT, basically, it's the same. OK? So GM1 equals, so you get this result. And this is typically the case because my early voltage or my this RO1 is much more larger than beta. That is typically true. OK? So what happened is that this would then lead to your overall output resistance. As I said, your would then be beta RO for BJT cascade. OK? So that will lead to a limitation as to how does one stack things up. So let me explain why. So if you talk about MOSFET and the difference between a MOSFET cascade current source and that of a BJT, one of the things is that if I'm not satisfied with this output resistance, what can I do next? I'm stacking 2. Can I stack 3? OK. So what happens if I stack 3 for the above solution? If you think about it, if I'm doing 2 versions, I'm just assuming they're having the same this is just a I just want to give you a sense as to what are the limitations of these two. So if I'm looking in from this 3-stack structure, what happened is that I could actually, assuming that if I'm looking in from here, I already know this is GM RO squared. Okay? So simply R out will be GMRO based on the same equation times another GMRO squared. Right? You amplify by whatever is the bottom resistance. This is RS. So this will give you GMRO squared times RO. So your output resistance being boosted twice when you cascade 3 layers of transistors. So what happened to the BJT version? If you think about it, so this is the MOS version. Let's look at the BJT version of 3 stacks. Q1, Q2, Q3. Okay? So if I'm looking down, I already know this answer. I already know that this will be beta RO. If you're looking down, it should be beta RO. So based on this equation, if I'm looking down from here, my RO should be GM RO. I'm just going to highlight 3 for now. Just make sure that you know that it's being amplified by the top transistor. And then following that, it will be RO, R pi, in parallel, beta RO. Okay? So what happened is that we know that if you compare R pi and beta RO, which one will dominate? Of course, R pi will be much, much smaller than beta RO. Therefore, the output resistance will then become GM RO R pi. Again, so it's beta RO. So that is to say that you only need to stack once for bipolar, because if you stack more, it doesn't help. The reason why it doesn't help is because it's in parallel with R pi. So this R pi would then dominate whatever is being stacked up, so it will not be able to boost it one step further. Okay? So let's go through 2 examples to, for us to understand a design of a cascade amplifier. What are the limitations? So once again, if I'm doing this, okay. A cascade current source. So there's mainly 2 features you want to see in your current source. One is its output resistance. The other is, I actually didn't plot it here, is because you want to know its operation range. So basically, you want to know when it starts to become flat. For example, this is VD set. So we know that it only works when it's above a certain biasing level. So this is the same. The example of cascade, the concern R1 is R out. The other is its VO minimum or maximum. So it's basically its operation or operation range. So these are typically trade-offs because when you actually doing cascode structure, you probably limit your operation range of being a high output resistance at the high output resistance range. So let's use an example of a pulling up version. So I'm using a PMOS. So let's say if this is my case, you need to find two parameters. One is its output resistance. One is VO maximum. If you're looking at pulling up version. So this is VDD. I'm having two transistors, well, 1, 1, and 2. And this is VB2, VB1. So I'm looking up to the top for its output resistance. And I'm also checking where is my VO maximum. In this case, because it would then, you want to know, because it's looking up, so you want to know where your ceiling is. Okay? So this will then be equivalent to a current source. Okay? So let me give you parameters, and then we're going to design to find our output resistance and its biasing design. So example, let me give the parameters. Let's say threshold. We're going to ignore body effect here because this one actually is subject to body effect as well. And lambda equals to 0.1 volts. And we want our I1 to be 100 microamp. And I'm setting my transconductance. These are given. This is given by design criterion, GM2 equals to 0.5 milliamp per volt. So these are the settings. So to achieve that target, we want you to first set VB1 and VB2 so that this is met. The other is to find its output resistance, of course. And lastly is to determine in that setting what is your ceiling, what is your maximum voltage, so that you're still operating, both transistors are still operating saturation. Okay? So first of all, anytime you have current and GM, the thing is that you allow us to set your overdrive. So you can use for part 8. Let me see where I'm going to move. Just give me a second. So let's start by determine its, we start part A. I'm just going to use this. So we know that GM can be expressed as, once again, we use this a lot, especially in design problems, because typically current is set by your target, and then you then have transconductance being set. So this is ID VGS minus VTH. That's my overdrive. So this would then give me, this is VOV. So we know that my overdrive will then be determined by ID divided by GM, because the GMs are known, current is known, so that this is 0.2 and this is 0.5. This will give me 0.4 volt. In terms of setting up the overdrive for both transistors. We're using identical transistors for now. Assuming that M1 and M2 are identical, let's say W over L1 equals to W over L2. Okay? And then, so this would then tell us that what is the voltage between, you can set VB2 now. So VB2 should be VDD, that's minus I should say VSG2. And what is VSG? VSG is, this is VDD minus a threshold of PMOS plus VOV. Just to be precise. It's a PMOS threshold because we're talking about PMOS transistors. Okay? So this will then give me, did I give the voltage? This is 1.8 volt. So this is 1.8 minus 0.5 plus 0.4. This will be 0.9. Okay? So this already tells me that this voltage set this bias to be 0.9 volt. Okay? So how does one determine this voltage, VB2, VB1? This one is already known, but this one, because this drain voltage or the drain voltage at this is undetermined, so it's set by your whatever you want. So typically you want to set it to the highest level, which is you want to set this point to the highest level so that this can be moved to the highest level. Therefore, typically, this is set to one threshold higher. So this, let's say Vx is set to VB2 plus one threshold, so that it will be at the edge, so that it will still be in saturation, at the edge of saturation. So it will be 1.3. Did I get it? 1.4 volts, sorry. You want to set to 1.4 volts, so it will be at the edge. So M2, let me write it down clearly. You set it to 1.4 so that M2 is at the edge of saturation. So sort of like you want to push it to the boundary so that they will give you more leeway for setting this up. If you set this too low, this voltage will have to go lower. Therefore, this voltage has to go lower. So this is to maximize your operation region. So remember, this is set by VB1. So VB1, therefore, I can write it down. So VB1 will be Vx minus VSG1, which is VDD, the same thing, minus VTP plus VOV. So it's the same 0.9. So this will then set this to 0.5. Okay? This will be 0.5 volt. So we already know where we want to set these two. So this would then, so if this is 0.5, what is your VO max? meaning that M1 will remain in saturation. So VO max will then be VB1 plus a threshold, right? So this will be 0.9. So I'm already at answer part C. Okay? So this is when both of them are at the edge of saturation. What is the edge of saturation is this. What I mean by this is this is the edge of saturation. So this is saturation. This is linear. I should say at the edge of linear it's the same, but because you're coming in from saturation, so this is the edge of saturation. Before it enters linear. So you don't want it to enter linear, otherwise all the model doesn't work. Your small signal model doesn't work. All the equation doesn't work. So lastly, we need to find out its output resistance. So its output resistance, we're going to follow its equation. So the equation is fairly simple. For part B, R out was simply GM 2 RO2 times RO. So what we need to do is to find, we already know GM is 0.5 milliamp per volt. We know that RO, there's only one RO, they're the same because they're the same current, lambda ID. So this is 100K. So once we have these numbers, we can find out that GMRO equals to 50. Get it right? Therefore, your R out is 5 megavolt. Okay? So you want to see that this is a very powerful tool to get large resistance. Because if you think about it, I've said it many times, is that it's actually very hard to construct resistance, especially to get large resistance in integrated circuit. So you typically wanted to use transistors characteristic to effectively give you this current source-like or high resistance-like behavior. So by stacking two transistors, much area, more area sufficient. You could think, if I give you some, if you ever did any tape-out examples, if I give you a resistor model file, for example, you will see that to create such resistors, 5 megaohm resistors is essentially impossible, or it's very, very area consuming. You use like a snake-like, routing to get very, very large resistance. You need a lot of routing area in order for that to be realized. So this is a very powerful tool for this to be realized. So, so if we look at current source behavior, as I said, there's two key parameters. There's always trade-offs. So if I ask you to draw the characteristic of this current source. So this is equivalent to a current source. You want to draw I1 as a function of VO. This is the current source. Okay, so let's say this is VDD. So there's a limitation as to where it can go because it's a PMOS, so it goes the opposite direction. As I said, it has an upper limit, VO maximum. So only when it's within this, from 0 to 0.9, so it's about half. So this is 1.8. In scale, you will see that This is 0.9. This is where you get RL 5 megohm, meaning very, very high. It's fairly flat because it's a very high resistance. Right? When it enters transition, so this is the region where both M1 and M2 in saturation. When you start to enter higher voltage above 0.9 volt, then either one of the transistors will become a linear, so you get degradation of its slope, and then it will look something like this. So you first get sort of degradation in its slope, and then it will go like that. So your operation region is fairly limited. This is VO minimum. This is your VO max. As I said, it's being set by VB2. Okay? So I want to emphasize once again the benefit of having a cascode is to have high output resistance. But the main trade-off is that it will lead to much lower operation. The analogy I would like to use is that a cascode structure for amplifier or even for having current source is like wearing a lot of clothes to isolate yourself from heat. So what happened from cold? But what happened is that when you wear a lot of clothes, it's very hard to move. So it limits your movement a lot because of this isolation. Anytime you do isolation, the cost is your freedom to move. Okay?